This is the APRS Podcast, recorded May 20th, 2015. Episode 250, with guest Vic Apria, Federated, Firmware, Functionalism.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And I'm Chris Gamble of Contextual Electronics.
And I'm Vic Apria of Wicked Device.
Hey Vic, thanks for joining us.
Hi Dave, thanks for having me. Appreciate it.
How is the air quality in here right now? Can you tell me how the air quality is?
Well, if you had a certain sensor...
It's an air of awkwardness with that question that I asked.
It is. Let's start with who are you and where are you from and how was your childhood and
My life story, huh?
Yeah.
All right, so I guess I've got a background of growing up in Connecticut and got my first computer at 10 years old or so. It was a Commodore 64. Got it from a yard sale.
There you
go. And then, graduated in my adolescent years to like a Hewlett-Packard PC. I believe it was a 33 megahertz PC, which was blisteringly fast for its age, right?
Yeah. That would have been a 386, or was it a 386 SX?
Yeah, I think it was a 486DX, actually.
Oh, screaming.
Yeah, I felt I was pretty advanced. I upgraded its cache for the front side burst cache to like 512K or something like that. So yeah, that's how I got interested in computers. The Commodore got me kind of originally interested in computers. And,
hang
also,
on. This was back when computers had cache memory. Cache, that's how we call it here in Australia. Cache memory, folks. You remember?
Yes.
Who remembers? Hand up, anyone who remembers the cache RAM scandal? The fake cache.
I don't.
I know. I'm not familiar with that.
You youngsters out there! Quick! Let me tell you a quick side story.
All right.
Yeah, it was this would have been like early mid-90s or something like that. A lot of companies out there, a lot of computer companies, started realizing that people didn't really notice the difference if their cache was installed or not. Right? So, and of course, I think the Chinese figured this out and they started manufacturing fake cache memory chips. Like they were fake SRAM chips that you'll plug into dip sockets on the motherboard. Right?
Okay.
And so so they started manufacturing these blank chips, or there was some other, non-functional chip, but you'd plug them in and they'd silk screen them so they would look like real chips, and you'd plug them into the board, and, all these companies were selling, all these computer companies, either knowingly or unknowingly, selling computers that had, 256K of cache or so. I don't know what size they were or whatever.
Air cache.
Yeah, and it was, they were air inside. There was nothing. And of course, you really didn't notice the difference unless you did real proper benchmarks and knew exactly what you were doing to figure out the difference. But then, the scandal broke and this was a huge deal at the time. Because, these SRAM chips weren't cheap.
Oh, yeah.
Right? So, So, a lot of these computer dealers, because margins were cutthroat back in the day, right? So they were going, you're going to sell us a bunch of cheap SRAM case chips? Fantastic. We'll buy them. And they're, fake. Oops. Anyway, that was fun. Back to your story. Sorry, that was a little nonsense.
Counterfeiting's been around for a long time, I guess.
Oh, yeah.
Very long time, yep.
It's not just in the news now.
Right.
I kind of got into computers at an early age because of that, and also took like an electronics course in high school. It was actually an electricity course, they called it. It was kind of like woodshop, right?
Yeah, right.
So they taught you how to wire a house, but by the way, here's about a dozen ways to blink LEDs with circuits, which I thought was pretty awesome, and then I went to apply for college and decided I wanted to be an engineer as a result of that class. I didn't know what I wanted to do. I wanted to probably either be a computer scientist or an electrical engineer. I kind of knew that from my electronics class and from kind of doing independent study on computer science because it wasn't really a subject they offered in school at the time.
Mm-hmm.
And so I went to university. I went to Cornell University. I went to Ithaca, New York, which is where I live now. I'm one of those guys that went to Cornell and stuck around, never left.
Right.
Now you're the townie.
I'm the townie, yeah.
Yeah.
Yeah, I went there for I went there undecided in engineering and kind of split my course load with computer science classes and electrical engineering classes. And around about my second year, I decided staring at the computer screen was less fun than getting in the lab and blowing up capacitors. So I decided to kind of try my hand at electrical engineering. And what really solidified it for me was when I took my first class in microcontrollers. It was the second year that they had offered that class. So I was in like the second class of it. And it's actually become kind of a pretty well-known class on the internet these days. It was taught by Bruce Land. It was called Introduction to Microcontrollers.
I was just looking at his stuff. Yeah, I was just because
he's awesome.
Yeah, he really is. Yeah, he's on because he's on the Hackaday project site and he's big on there. And I was looking at his YouTube channel. He does like videos of all his student stuff. So
right after I left, he started actually having the course filmed and put online. And I thought that's really great.
That's cool.
And actually, like the project pages on that course are still available, like the historic project pages, and they are an amazing resource. Because we have,
especially because it's like right at that level where it's like where you'd want to be, like if you're kind of getting launched into it, all the pitfalls that other students might be having, that kind of thing.
Exactly. Yeah, and you can see sort of. You can read the projects at a high level, and if you want to dig into it, most of those projects all have their source code and schematics and everything up there as well, which is great.
I will have to dig in.
Yeah, it's cool. So we for my final project in that class, me and my lab partner, we made a vertical plotting machine. So you hang that from a whiteboard. It has two stepper motors at either corner.
Right.
And so through stepping the different motors in this kind of triangular space, you can draw rectilinear things, right?
All right.
So our great accomplishment there was, our culminating thing is we had some kind of a push button keypad interface with an LCD, and it could you could type in the coordinates that you wanted it to draw to, and we made it draw a square, right? No, it was no big deal, but it was actually really a lot of complicated math that went into that. And the funny story that goes with that is years later, I would go to a maker fair, and I encountered this high school student who had a very similar looking thing, but it was drawing works of art, right? Like it's called the drawing machine, I think. And it was like mind blowing. And I was like, wow, that looks a lot like my project. So I went and talked to him, and he actually said that he came across our project page as a inspiration and resource. I was like, wow. Well, and he had done it with an Arduino instead of doing it with we had done it with like bare AVR GCC code. And I mean, it's just amazing how much the barrier tree has gone down so that you can do so much more from the ground level, right? So that's great. So that's kind of how I went through college. I guess as a I got out of college around 2002 when the job market was pretty soft. So I stuck around for a while to get a master's after that in engineering. So it was really an excuse to take more coursework that I didn't get around to in my undergrad.
Yeah. And people don't know too. I mean, Ithaca. I mean, sorry, Cornell. It's Cornell, right?
Cornell.
Yeah, it's in Ithaca.
It is.
Yeah, I mean that's a great school overall, and I mean there's a lot of good people that came out of there. So
yeah, it's a bit rural. Actually, cool thing. You guys talk about like Shannon Nyquist theorem and things like that, the sampling theorem. Yeah. Shannon was actually a professor here, I think. I'm pretty sure. Anyway, that's my favorite famous reference.
Don't worry, we do maybe history all the time around here. We're pretty sure that this historic thing happened.
I'll leave the audience to do the fact checking.
Yeah, right. Our comment section is our fact checker.
There you go. Yeah. Yep. So actually, while I was a grad student, I had a kind of a unique experience where there was a course that I had taken that a faculty member that would have taught it normally left kind of suddenly to take a position at another university, and they were kind of, the department was in kind of a spot for finding a lecturer for it. And so I got approached by my advisor to say, hey, could you take a semester off of your grad work and teach this class? So I said, yeah, sure. I've got no rush to get out of school. So I did that for I did that for a semester and a summer. So I taught a course in computer architecture. And I didn't do really well in the course when I was an undergrad and I took it, but I knew it backwards and forwards by the time I finished teaching it. So that's kind of, that's kind of, and, yeah, I'm sure you
forces you. Yeah.
I'm sure that's you've got a lot of similar experiences probably with contextual electronics, right, Chris?
Yeah. Oh yeah. I'm clueless sometimes, but not at the end. By the end, I'm an expert.
Yeah, exactly. Well, it's always a lot more pressure to know the right answer, so you study harder.
Yeah,
when the kids and students are trying to get answers from you. So yeah, I did some teaching, and I really enjoyed the teaching to the point where I was actually thinking about trying to stay in school even longer and get a PhD. But ultimately, I decided to go into the workforce, and I went to work for Lockheed Martin, which surprisingly is in Owego, New York. They have a big site there, and it actually was like the original IBM facility. That's where IBM started in Endicott, or as they say in the Southern Tier, Endicott. And so I spent the last 9 years there till last year, and did a lot of work on cockpit controls and displays for helicopters primarily.
That's pretty cool.
Yeah, a helicopter is a pretty wild beast. And the navigation,
a lot of subsystems and crazy stuff, right? There's
all sorts of inertial navigation systems, and all these things kind of get integrated in glass cockpits now. And so I did a lot of work in sort of designing displays, doing integration and test on them, and I kind of had the whole tour of things you could do at Lockheed at the site in Owego anyway.
Yeah, right. That's interesting that I like. Why New York for that kind of thing? I mean, it's just proximity to. I mean, that's not that close to New York City, though, right? I mean, giving geography wise.
No, it's 4 hours away from New York City. It's in the middle it's like right in the middle of the state. Yep.
Yeah.
And so I think it's probably a heritage thing. Like, it started as IBM Federal Systems, I think. So they had a government connection, and then over the many years of kind of mergers and acquisitions and yada yada, it ended up as Lockheed Martin in like the late 90s.
Yeah. Well, and if you have talent that kind of, if IBM attracts talent around the area too, it's like probably makes sense for other companies to come in and do the same thing there.
Right.
You know.
It never ceased to amaze me as well. Just kind of the level of there's some amazing people in the Southern Tier, but like you said, because of IBM. I think it's also there's like the culture surrounding that was. People that were working there had been working there forever, right? Like for like 25, 30 years.
Yep.
Yeah.
It was not uncommon at all to see like 25-year veterans there.
Right. Well, and it's like, I mean, the same thing happens at least around here, and I'm sure Dave could say the same thing in Sydney too. It's like when there's only so many jobs in an area, you know, you can bounce between them, and unless you want to uproot your whole family, which, you know, not a lot of people choose to do. It's like that's a big change.
Here in Australia and Sydney, we just don't have the same culture of moving that you guys do. It's like you live in Sydney, you find a job in Sydney, you don't go, oh, there's a good job going in Western Australia, I'm going to move to Western Australia. It just, like very few people actually do that. It's, whereas you guys have a different culture of moving, especially for study as well, which we've talked about before, whereas we don't do that. You just study near where your home is. I mean, that's,
that seems like a starker contrast, though, because I think a lot of people move for study, but I think less so. I mean, maybe I'm wrong about this, but I mean, I think the people that I know, when they start, settling down, having families kind of thing, it's like more stick in the area unless something huge comes along or there's some, big event kind of thing, so.
Right. Mm-hmm. Yeah. And so in the sort of in between going to work for Lockheed and finishing up with education, I guess part of why I left education was because I met my wife in college too, and we got married here in the region as well, and bought a house, kind of settled down, right? So we really enjoy the environment in Ithaca, and if you can survive the harsh winters, the summers are beautiful.
Right.
Yeah. So let's see. So that takes us kind of into.
Also, we should at least mention Southern Tier Brewing as well. I mean, that's like one of the best breweries in the country. So.
Yeah, but there's also a good beer company is Ithaca Beer Company.
That's another good one. Yeah,
little or known, but they're very good.
Right. I guess.
Yeah. So let's see. So around 2010, while still working at Lockheed, I met a friend through my wife's book club, actually. The husbands of the book club, right?
Right.
Natural, yeah.
So we
who hasn't met someone that way?
Yeah, exactly. So we got to talking, and we had a kind of a shared interest in electronics, and he was telling me in 2010 that he had heard of this thing called Arduino, and I was like, he got to describing it to me, and I kind of got on my high horse about APRs and how I could program them without an Arduino.
Yeah,
and,
right.
But eventually he convinced me to kind of have a closer look at it, and so we kind of got together on the weekends and started doing hobby projects together, just to kind of, as when you go to work for a big company, a lot of times you don't have you lose some of the enthusiasm for coming and doing it at home. But I did remember, that I really did enjoy working on electronics, sort of in my leisure time, in my sort of younger years before I went to work, and then so that gave me the opportunity to kind of like get re-inspired a little bit about electronics, and I had this project that I had in the back burner that I always wanted to do while I was in college, but never got around to it. It was a binary clock, which is like something everyone should make, right?
Mm-hmm.
Right.
We made a binary clock as a project, and I had never done much PCB design as a student, and so it gave me kind of a chance to get my feet wet on that area a little more as well. So we designed a PCB in like one of those really garbagey CAD tools that was
like the free ones from
like the proprietary ones from like whatever PCB Express, right? That doesn't even generate Gerbers or whatever. It just generates like order now.
Yeah.
Which is kind of ironic, right? Like some of these web-based tools are sort of, that's kind of the model they're leaning towards, right? Is like click a button, get your board. What's the Gerber file? But yeah, so I made it originally in that, and had this sort of had this sort of usual snafu of let's go make some of these, and oh yeah, I forgot to connect these two ground nuts because the tool doesn't tell you that you didn't do that. And so I had right out of the gates kind of had my first made a mistake in the PCB layout kind of a thing. But shortly thereafter, I was like, okay, there's got to be a better solution to this than these garbage tools, right? And that's where I found Eagle, right? Like many of the sort of people around the same era, looking on the internet. Eagle was pretty popular at the time. There was no such thing as KiCad. And there was
there was.
It was called Jita. Yeah, it was called Jita, right?
Nobody used it.
No, that's different.
It's different. Yeah. But nobody used it. It wasn't as big as it is now.
Oh, KiCad's been around that long.
Yeah.
No, I didn't even know
Technically
that.
started in 92.
Oh my gosh.
Yeah.
Learn something new every day.
2007 it started, yeah.
Well, it wasn't on the radar, I guess, in terms of
right.
popularity.
And it wouldn't have been very useful, probably.
Yeah. So I went ahead and I kind of said, okay, well, Eagle seems like a much better tool. I'll pick that up, and I kind of what's the word? I guess I kind of got my introduction to PCB design by fire through Eagle, right?
Oh yeah.
And so many so like I've heard you guys say and other guests say many times, it's like the tool that you learn is the tool you stick with. So
yeah, pretty much.
Yeah, I mean, like, and I didn't do really any of that kind of thing, like layout in my professional life, or schematics. And it's kind of interesting, right? Those are like the people that do the schematics are not the people that do the layout in the industry. They're all different people.
Yep.
It's all sectioned off, and so I kind of
It depends on what company you work at, but typically at a military company, I've been the PCB layout person.
right.
You know.
Yeah, it's
exactly.
just super pigeonholed because the demands are so much higher for super fancy boards,
Right,
stuff
and
like
you use
that.
these big cadence package, cadence and mentor and all these big like packages that you couldn't possibly ever get your hands on outside of work, kind of a thing.
Yeah.
And so I did get the chance to do some kind of test equipment work in my later years at work, and I like that better, where I was able to convince some R&D manager to say, hey, get me a license of Eagle. I can do the layout and the schematics and get this done without all this kind of back and forth rigmarole with the different parts of the house doing the job. And so that was kind of fun, but it was just kind of picking and choosing spots where you could actually do that because it wasn't critical and process could be tailored, right? That kind of thing.
Right.
So back in like my hobby work with Dirk, who's the friend of mine from the wives book club friend, right? Dirk, we kind of kept doing things on the weekends and evenings, and we kind of got to thinking that maybe these projects we were working on could be turned into kits, and maybe other people might want to buy them. So we took the binary clock project, we called it Minty Time, and because it fit into an Altoid stand, as tacky as that is. And we basically put up a website and said, let's see if people would buy these things, right? And so all the work that goes along with that in terms of, okay, now we have to actually make a website and all these other things that are not electronics, right?
So was this a surface mount kit or a through-hole kit?
No, the Minty Time kit is totally through-hole.
Right.
And I would individually program the chips with an ISP programmer and stick them into black styrofoam and all that stuff, right? And it's that's where you learn that like kits are not cheaper than
you don't want to be doing that.
Right, because it takes a ton of work to cut resistors into lengths.
I know.
Yeah, so we nevertheless continued down that road and made a bunch of other kits. We've done some work on using like ASK radio transmitter receiver pairs, and
is that the Minty Mote as well?
Yeah, so it's Minty Mote, and there's also that's actually Minty Mote is just a derivative of the base products that I started with, which we called it like a wicked node and a wicked receiver. And they're just like dumb ASK radio and modulator demodulator kind of things. And
are you a ham holder? Are you a ham license holder?
I am actually. That actually harkens back to another story we can go into if you want, which is I got my radio license while doing a amateur ballooning project. So
right.
Yeah, we can talk about that if you want. Let's see. So while I was at Lockheed, there was a kind of an engineering program that I got into, which had sort of extracurricular project work to do, right? And so the project was prescribed that we would make an amateur radio frequency controlled high altitude balloon to take pictures of the nape of the Earth, right? Like the high altitude ballooning kind of project.
Right. Yep.
And so we designed everything to do that from bare metal, basically. Kind of actually is tangent to what we were talking about on email, Chris. It's about like the multiple MCU function.
Yeah, we'll talk about
things.
that later. I'd like to talk about that in a little bit.
Sure.
Yeah.
So we actually put 4 AVRs into that payload. One of every AVR was controlling its own function, right? There was one that was talking to a VHF, UHF radio, and there was one that was talking to a camera, and there was one that was talking to a GPS. And they were all talking to each other over I2C. And so, so that's how I got my amateur radio license. And that was like a 5-year mission that had team handoffs from year to year. I actually ended up staying on as an advisor for the whole time, pretty much.
so this was done through Lockheed or through something like
it was like an educational joint venture with Cornell, like through a leadership program, basically.
Oh, okay.
Yeah.
Okay. And so how many of these things actually? And what time frame was this?
So this was I wonder if it's on the line still. It was called Project Blue Horizon. Let's see. It was like 2000. Let me see. It would be like 2006 through 2009, 2010, something like that. Yeah. If you look for Project Blue Horizon, I think, I don't know. It might be polluted with a whole bunch of other stuff now.
Okay.
But anyway,
that's good though. I mean, so this was just as basically a way to kind of do technical talent around a shared goal kind of thing.
Yeah, it was like it was kind of like right. It was a way to kind of encourage engineers to develop their skills and talents, and one way to do that is to fly balloons at up to 100,000 feet, I guess.
Yeah.
Yeah. So that was, and it was, there's also all sorts of other tangential stuff to doing that besides filling a balloon with helium and letting it rip. You have to actually kind of track the balloon, and it was actually really interesting.
You guys designed all the systems as well?
Yeah. We wrote software and used off-the-shelf software, and we designed hardware. We had to design so the requirements on ballooning are that, like the FAA requirements, I guess, are that you have to have like a cut-down mechanism, a primary cut-down mechanism, and a secondary cut-down mechanism to be able to abort the mission. And so
that's like the balloon popping itself, or what?
Yep, that's one. So it's like
it's headed for North Korea, folks. I think we'd better scuttle it.
Yeah, exactly. And the other way is kind of open to your discretion, and there's a lot of different ways people have used, like using nichrome wire to burn through the load line. We actually came up with a slightly dangerous way of doing it.
Dynamite.
Kind of. Actually, we filled it. We ended up making filling.
We used hydrogen, we used hydrogen instead of helium.
Yeah, we made a Zeppelin.
Made a Zeppelin. Yeah.
No, so what we actually did is we filled a like a pencil, like a like a mechanical pencil with black powder.
Yeah.
No, really?
Fed an electric match into it. And triggered it through software, right? We ignited some black powder, like packed into a pencil, to have an explosive link, basically. And so
I can tell you how we did several things like this in the military stuff, for underwater stuff. When our sonobuoys would hit the water, right? Of course, they had to activate, and then they had to activate the bag, right? So you had to actually fill the bag up instead of burst it. But you did have to burst it later. I'll tell you about that in a sec. But yeah, we had to fill it. So how we did that is we had a cylinder with with the gas. I can't remember what it was. Anyway, it was a pressurized cylinder, and then a little spike thing on top that was held back with a spring, and then held back with a string, which was then tied around a 2-watt resistor.
It sounds like a Rube Goldberg machine here.
Yeah. This was highly engineered and tested, by the way.
Yeah. String is highly engineered. Was there duct tape in there too, Dave?
Oh no, it was a fishing line. I can't remember. Anyway, we qualified that string to the hilt. We took months to qualify that string. Anyway, so we'd wrap it around the resistor, and then the batteries, once the salt water battery detector was activated, then it would pass current through the resistor would heat up, it'd burn through the string, and then the spring would go down, boom, it'd burst the cylinder,
crazy,
spike the cylinder, the bag would inflate, and then everything's happy, and then 8 hours later, it had to scuttle itself. So when burn another resistor, which was in a little pocket on the side of the flotation thing, and that would burn a hole in the flotation bag, and then the thing would sink to the bottom of the ocean.
Wow.
So, yeah.
Totally a Rube Goldberg device.
Yeah.
Actually,
but there's an amazing amount of engineering which goes into qualifying and testing and actually designing that, and the thought process that goes through to, okay, this is the best solution.
Yeah, no doubt about it.
Yeah.
A lot of hours are spent coming up with the perfect way to do something, or the best way to do something.
Yep, totally.
Actually, I don't encourage this, but ping pong balls filled with black powder do some amazing stuff when ignited.
Right.
Now we're getting to the good stuff.
Yeah, we weren't sure what the best kind of link mechanism would be to like tie a string to on one end and tie a string to on the other end and pop it in the middle. And ping pong balls expand to an amazing diameter before they explode.
Really?
Yeah, it's crazy.
Good video of this?
Well, oh no, we didn't get any video of it because we were kind of sheltering ourselves behind a garbage disposal area, hiding from the blast, kind of a thing.
Right.
Getting your hands on black powder is also kind of an interesting experience if you're not a hunter.
Yeah, I was gonna say, I'd figure with muzzle loaders it would be pretty easy.
Yeah, but we ended up having to drive into the middle of nowhere to like a gun shop. We're like, I'm not like an outdoor enthusiast or anything. It was kind of, going out into the backwoods to get gunpowder was a kind of an interesting experience.
Old Cletus selling you some gunpowder.
Yeah.
Well, you want to buy some gunpowder, do you?
Oh man, I'll never forget it. It was like some guy's house. You go Googling it. It's like some guy's house.
No, Vic, it's a registered gun shop.
Exactly.
That's how you get around the rules. Yes.
Exactly.
It's official.
So
It's like
weird.
yeah. They were having a gun show that day, of course, and that means that you don't need background checks or something ridiculous like that.
You're right.
Totally.
That's fun.
So anyway, we actually did get some really cool pictures that first flight. We got up to 100,000 feet, and over the course of all these flights, there was I guess there's actual records on all this stuff, and when flights go up, you're supposed to register with the organization. I think that the project itself actually ended up having the record for the highest balloon flight and the longest duration over the course of some amount of time. One of them actually grounded a flight in Nova Scotia.
Oops.
Yeah, whoops. It almost caused an international incident kind of thing, right?
Really?
How
are you supposed to do that? You're supposed to notify?
So we had GPS track on all of these flights, and one of them was starting to go right towards an airport in Nova Scotia. I guess the airport, right? There's not many. And so like when we had to kind of make the call of like calling up this airport and letting them know this thing is on the way, and here's the way you can track it and everything else. And they ended up actually delaying a flight because of it, which was
Wow.
interesting.
That's got to be an annoying thing if you're on the plane.
Yeah, I'm sure.
Folks, we've got a weather balloon.
Yep.
bunch of nerds are doing experiments here. And,
you know what's crazy though? There's like 1,000 balloons that go up every day.
Like day?
Oh yeah,
It's insane.
There's weather balloons, military and civilian weather balloons alone.
Yeah.
There must be hundreds. Yeah.
Uh-huh,
Really?
Exactly.
Yeah,
Just
yeah.
just to get weather data, right? To get like
Yep.
for the flight traffic and everything else. I was amazed by that.
That's how they actually pass back that. Are they like reusable, or
I think they
this
just
doesn't
go
really
off.
compute for
I
me.
think they just go out and never come back. Like they end up crashing somewhere and whatever.
Huh.
Yeah.
I didn't know that at all. That actually is really interesting.
Yeah. Again, I'll probably be fact checked on that, but it's a lot, and we actually got community involvement like across. There's a whole like subculture of doing this kind of thing, I think, and this high altitude ballooning, and
Like within the ham or within.
yeah,
just,
there's a
just
lot.
like
There's a
separate-
lot within ham. I think most of the projects actually have ham connections.
Yeah.
And so we actually hooked into this network called the APRS Network, which people might have heard of. It's like I think it stands for Amateur
yes.
Radio Positioning System or something like that.
Yeah.
And so
Hang on.
Okay.
I've got data.
Yep.
I've got data. NOAA, the National Weather Service, they release 70,000 radio sons every year.
Every what?
Whoa.
Every year.
Yeah.
Every year. 70,000. How many is that? Divide by 365. How many is that a day?
Let's do
Hang
some
on.
quick math
Don't
here.
have my calculator.
I'll let you get to it.
I've long since given up doing arithmetic.
191 a day.
Yeah.
And that's just one
and
organization.
they only recover about 20% of them.
Right.
Wow.
Yep.
Yep.
That's nuts.
I mean, if they go out, I mean, a lot of the winds are often west. They're easterly winds. They head towards the Atlantic usually, right? So if you're on the coast, those things are just gone.
Yeah, I always wonder about have you guys ever been on hint.fm before?
No.
Nope.
There's a wind map you can look at, and I'm sure there's other ways of doing this. It might just be like ground and stuff like that. It's actually really beautiful visualization. It's hint.fm/wind, and you can actually see live data.
Cool.
Of wind stuff, and so maybe this is just ground, but I always just wonder about how this kind of data is collected, and if it or jet stream stuff, stuff like really high up.
Yeah.
Maybe that's probably a bigger one is high up stuff.
Well, you just do the GPS, right? You put a GPS of some kind on the thing, and you track its movement. And actually, it's actually crazy. The winds do insane stuff on the way up, right? There's shearing. They change directions radically at a layer boundaries. So yeah. I always wonder about that too. Again, another outside link, but recently they did the. Have you guys seen the Jetman? You ever seen Jetman before? No.
The guy, it's this French guy who basically wears a carbon fiber wing filled with fuel, and he can
yeah.
sky.
Right.
And now there's two of them, and basically they're commercializing this flight method. But they're just up there, in terms of like wind and all those controls, that's I know some pilots and so they tell me about that stuff, but that's still that's a bigger thing, that's a bigger device, and so I can only imagine like you said with those shearing forces and stuff like that, it's got to be just nuts.
Oh yeah,
I mean, I don't know if it's based
just imagine if you're sitting in a plane and you look out the window and there's a guy going past in his rocket backpack.
Yeah. That's amazing. I can't believe someone would do that.
Yeah, no, there's it's a video that just came out in Dubai. It's unbelievable. They're flying around the Burj, that the world's tallest building. They're crisscrossing around it. It's
I would totally do that.
Oh yeah.
I would totally do that if I had 1 week to live.
Right.
I would totally do that.
Right.
Yeah.
But maybe even if not, I mean, if you're good, I mean, I don't know.
Well, a balloon in the jet stream could get up to 100 miles an hour just being there, right? Just based on the winds. Oh yeah, easily.
Oh yeah.
Wow.
Easily.
What about temperature stuff? I mean, how
that's also
you
pretty
cool.
Oh, you don't want to go above 10,000 feet.
Actually,
you'll freeze to death before you.
So that's really
that's
really interesting actually. So I didn't know this either, but there's there's a temperature inversion thing that happens as you go above a certain altitude, and the ozone thins, I guess. You start getting hot again.
All right. Yep.
Oh, because you lose shielding from the
right. You get more radiant energy, I guess, from the sun that's not lossy through the atmosphere. Yeah. So there's sort of I wish I had all the data from it still, but I'm sure it's actually out there somewhere.
Oh yeah.
Well, who we need to get on the show is Felix Baumgartner, if that's how you pronounce his name. We need to get him on the show.
Okay.
Come on, tell me, Chris.
Oh, is that the guy that jumped? Oh, that's the guy that jumped out of the weather balloon.
That's the guy that jumped from 120,000 feet. Yeah.
Right.
No, that guy's nuts.
Yeah.
Red Bull.
Fine line between crazy and brave there.
Yeah.
Oh, we need to get the original Army guy. I think it was an Army guy who did it. Felix broke his record, but he did it back in the 1960s with just a leather, aviation helmet and a.
Back when men were men.
Yeah, exactly.
And calculations were underdone for jumping out of a weather balloon.
and he jumped from 100,000 feet or something, and it's crazy.
So another kind of weird thing with that I was worried about with GPS in the balloon was I had read things that said that they would disable themselves above some altitude, and we wanted to get up over 100,000 feet, and I think this is true actually. Again, I'll be fact checked, I'm sure, but I think if you're going above a certain speed and above a certain altitude, GPSs have to shut themselves down. So if you're if you look like a missile
regulation?
guidance system or something, then I think they're not allowed to work. So as long as I think we were okay because we were a slow moving high object. But I think that there's
but who's gonna know?
Well, I guess you could always get a non-compliant GPS or something, right? But I think all compliant GPSs are designed to kind of self-police or something.
Got it.
Yeah, that was an interesting sort of.
Sounds like we need to test this now.
Yeah, right?
It sounds like we need to launch something very quickly.
I don't know if that's a good idea.
Yeah, fine.
I mean, what's the worst that can happen, right? You just kind of lose whatever it is, but
Yeah.
I guess
Anyway,
the worst
from-
thing can, yeah.
From high altitude ballooning to eggs,
right. So what?
which is what we got you on the show for.
Right. So
Yeah, eggs, that sounds normal. Just balloons, eggs. They're both kind of white and roundish,
Right.
but not white quite.
Yep.
Yeah.
one of them inflates to a much bigger diameter.
Yeah, right, right.
Oh yeah. So okay. So let's see. Where were we? So around 2012, Dirk and I got involved in sort of a community of people interested in air quality, and wanting to do a project that would enable more people to collect more data, so that we could have a better picture of what air quality looks like in different environments, rural and urban environments across the globe. And so there was a lot of involvement in kind of meetups in the Netherlands, in London, in New York City, and we ended up going to a meetup in New York City, and kind of getting together with a couple of guys we knew through a lot of indirection, but Joseph Saavedra and Ed Borden kind of were the evangelists, I guess you would call them, of this community, and they had this idea, this new it was kind of a new thing at the time. This Kickstarter was out there, and they wanted to do a Kickstarter and to reach a broader community audience and get these sensors sort of out into the field and see what would happen, kind of a thing. And because we knew these guys through we had worked with a fellow in London, Ken Boak, who had made a board called the Nano, and that's how we kind of indirectly got connected to Ed through Patchy Bay, which is the company that has since become Xively through a couple of other name changes.
Yeah.
But the point is that we kind of got tapped as the Dirk and I got tapped as like the sort of the engineering behind that project, and so we kind of agreed to go ahead and see what would happen with the Kickstarter, and it ended up being kind of a crazy couple of months where we kind of planned out what this would be, what kind of shape it would take, what it would cost. Joe did a bunch of work on sort of breadboarding and proving out the technologies, these metal oxide semiconductor sensors that were low, they were relatively low cost compared to sort of the things you would find at an EPA government site or something like that. And we wanted to make them be internet connected and be connected to kind of a global pool of data that people can analyze. And
now, what are these sensors actually measuring for?
So what they're actually doing. Okay, so caveat: I'm not a chemist, right? But this is chemistry essentially that's happening.
Right.
They actually
you know voltages when it comes off the sensor.
Yeah, right. Actually, resistances, as it turns out.
Oh, interesting.
Yeah.
Okay.
So what happens is that they're kind of glorified variable resistors that have heating elements on them, and the semiconducting material kind of inspires at a certain temperature a selective reduction oxidation reaction, right? Like a redox reaction.
Right.
And certain gases are reducing, certain gases are oxidizing. And when they reduce and oxidize near the surface of these wafers, under the right temperature conditions, they are selective to certain species, they call them. This is all stuff kind of I've learned in the last few years.
Yeah.
But the gist of it is that in the presence of a target gas, they will change resistance in fairly dramatic ways. Okay.
And what type of gases are we talking about? What
Right,
type? What
got it.
constitutes bad air quality?
Got it.
Is
Yes.
what I'm getting at.
Got it. So the common pollutants, the EPA has kind of spelled out some guidelines on what the air standards are. They're called the NAAQS, the National Ambient Air Quality Standards, I believe is what that stands for. And the gases that they've identified as kind of important to pay attention to are nitrogen dioxide, carbon monoxide, ozone, particulate matter, which isn't a gas, right? But it's sort of a nebulous term. But and I think lead is also on the list, which I don't really know that much about yet, but I'm guessing I will in the next couple of years. Those are sort of the species in question. They're usually like sort of the byproducts of industrial processes and automotive exhaust, that kind of, like,
which is
coal
the main
production,
driver.
right?
Yeah,
Exactly.
that's the main driver.
Right.
So do you need a different sensor for each one, or can one do multiple? Species.
So you can you typically have to do one per sensor, right? I wish they were that selective though, right? Because like inadvertently, I think you end up getting cross sensitivities between gases, and being able to separate those effects is non-trivial. So in the air quality egg, the baseline gases we measured with the unit was NO2, nitrogen dioxide, and carbon monoxide, and we ended up coming up with, in the midst of the excitement of the Kickstarter, there was all this like chatter. They wanted more gases and more add-ons. Basically, we had to come up with a way to like satisfy this new demand.
Species creep.
Yeah, species creep, exactly. I was like, oh yeah. When I signed up to the project, I was like, oh yeah, we can put that together. We've done work with Ethernet connected Arduino stuff, and we had an idea about what it would look like. And then I had to kind of bend my mind and think, how can we do this without designing 5 products now instead of 1? And so I kind of dreamed up an architecture that would allow for that without growing cost and everything too much, right? And so what I did is I ended up making a I guess you'd call it an abstraction layer where the sensors would host their own microcontrollers and be discovered by the main controller. And we were really kind of confined by some of the technology of the time as well, between the cost and the technology that existed, right? Wi-Fi was...
Wait. This is 4 years ago? 5 years ago?
Yeah,
exactly.
Actually, it was less. It was like 2012, right? It was like 3.5 years ago.
I guess that's kind of crazy. Yeah, I mean, you think about what's kind of come on the marketplace.
It's insane. Like the prospect of putting Wi-Fi onto a microcontroller back then was like, no way. Not for the price we were talking about, right? We were kickstarting. The Kickstarter was like targeting $100 rewards, and
well, it would be, you were looking at doing it on the micro, not micro adjacent, like with a lot of the modules that we have today.
Doing what on the
You said putting Wi-Fi onto the micro. But you meant like...
Right, I meant like putting in a Wi-Fi link on the product.
Yeah, okay. In the whole project, yeah. Okay.
So we ended up still having to solve that problem because, not everyone has an Ethernet cable they can run out to their backyard to plug into the internet.
Right.
like probably no one has that, right? So we ended up actually creating we used the RFM12B radios, right? They're FSK radios, and they're in the ISM band, so they're unlicensed. And so we ended up making a 2-unit solution where the outdoor unit would transmit over radio to the indoor unit, and the indoor unit would have a connection to an Ethernet and publish it to the internet.
Right.
It was like 4 hops to get from sensor to the internet.
And it sounds like you've blown your budget.
Oh man.
Yeah.
Yes, it was a challenge. It was a challenge.
Right, so is it fair to say this Kickstarter didn't make any money?
I think that's a pretty fair statement. I'd say
There
was a lot of sweat equity that you can't even possibly account for.
Oh no.
Yeah.
But if you ignore labor and everything else, just purely on cost of hardware.
I think it's pretty. There's probably it's not hard to deduce that based on the fact that like once we got through the Kickstarter and shipping them, we made the price go up quite. From $100 a unit to I think we went up to like $185 a unit. Because
Now this is the thing that you shocked us with when we were talking just before the episode. You got 927 backers. So you had to make like 1,000 of these things, which is reasonable enough volume, but not high enough to warrant what you bought.
Right.
Tell us about that.
Yeah, exactly. Well, all right. So first things first, right? The original goal of that Kickstarter was way lower than that. We were trying to just make a handful of them, but there was a lot of excitement around it at the time. And so we ended up kind of getting 5 times the demand. And probably the price point had a lot to do with that, right?
Right.
Maybe if it cost more like what it actually needed to cost, we wouldn't have gotten as much demand. So it's all a trade-off. But so can you say the question again, Dave?
Oh,
He's asking about the manufacturing.
You bought something to help with the manufacturing for 1,000 units.
Sure. Yeah, right.
Seemed like a good idea at the time.
Here's the sort of the background of that. So the Nano, which is what we were basing the product on, it was basically an ATmega 328, the Arduino staple processor, coupled to a microchip ENC 28J60. I think I got that right. Ethernet controller. So it's like a SPI Ethernet controller that integrates the PHY and the MAC and all in a chip. It's kind of a nice abstraction to the microcontroller. And up to the point of air quality egg, there had only existed a through-hole version of it, right? So we were like, okay, if we get like 100 backers, we can put together 300. We can put together all of these by hand. It won't be that big a deal, right? But then we got all this demand. It was like suddenly the prospect of soldering by hand these fairly complex boards, right, that were all through hole, became much less appealing at 900 units, right? So I actually went back to the drawing board and I actually turned it into an SMD design, with the thought of let's get this thing produced by a contract manufacturer, right?
Yeah.
Well, again, like you just said, the volume we were talking about is this horrible kind of twilight region where
it's the dead zone.
So bad.
Yes.
And so we went shopping around, and we didn't want to. Well, I mean, it wasn't practical. I was not about to kind of hand over a huge check to somebody in China that I'd never met, and I'm not going to fly to China to manage it. So we were shopping around locally and in the States, and it was forbidding. Right, the prices we were getting were like, okay, we can buy the boards, and then we're not going to have an enclosure, or we're not going to, we're going to have to like cut so much stuff.
Right.
So we made this sort of hard choice to say, well, if we're going to spend that much money, we may as well do it all, bring it all in house, right? Well, so we went out and we shopped around for a pick and place machine, and we got a secondhand pick and place machine from Mancorp actually. I think it was a similar machine to the one that Adafruit originally got. And so we bought a pick and place machine. We were like, okay, I guess we're gonna figure out how this works now. And we dealt with all the sort of growing pains of that, which it's not what you think it's gonna be a piece of cake, right? It's because it's a machine. The machine's gonna do what you tell it to. There's not gonna, but it turns out, right? These machines take a lot of babysitting. Getting them to work the first time takes a long time. Getting them to keep working once they are working takes more time. And then when you really kind of start sinking your teeth into it, it's like, oh, you need more than a pick and place machine to actually make boards. You need a reflow oven. You need a kind of, before you know it, you have like,
you need a stencil machine.
God. You're right. You get to the point where you're like, oh, these Mylar stencils work for about 10 boards, and I have to make 900 of them. Do the math. So yeah, you get into like, okay, now we have to figure out how to make aluminum screens and all the rest. But you know what? It was a really good experience. I wouldn't take that back, right? Because now we know a whole lot more about manufacturing.
So how long did it take you to actually get them all produced then?
So by Kickstarter standards, I'd call us Kickstarter on time. We were 6 months behind the actual deadline, but but we actually got them out the door by.
That's on time.
That's on time, right? And I think actually, all things considered, that's remarkable, right? That we we kind of went into this thinking we would use a lot of things that we already had, and ended up having to like spin boards out of thin air, right, to make it actually happen. So
can I just do a small boast here? I believe I am the only Kickstarter in history, I'm sure I'll be corrected, that actually shipped the same day the money came into my bank account.
That's awesome.
I know. I thank you. Yes.
I think there's probably
There's
probably a few more that have done it since, right?
Right. Yeah. Maybe. I didn't ship them all, of course, but I shipped all the ones that I said I like the early backers.
Right.
You know?
Right.
Yep.
Yeah, that's
the exact day.
That's
and I'm ready to. I was so
that is
proud
a great
of that.
accomplishment. I commend you for that.
Yep. Hand assembled.
Yeah. Right. Yeah. So for us to get them out the door in 6 months took a lot of like friends and family volunteering, packing boxes, picking up soldering irons and stuff like that. So,
and it's only 1,000. People have to remember it's only 1,000 units. That is not a lot.
Yeah, but you know what? The other thing you have to keep in mind is making 1,000 things doesn't mean making 1,000 things that work.
Yeah.
There's a little difference there. And when you have when you have a system that's made up of multiple boards, it's like a system of systems, failure, all these things that you don't think about. Yeah. Kind of.
So did you have fixturing and testing for all the? Because you said you had a micro per sensor board as well, right?
Right. So
how are you doing? How are you doing like firmware load there?
Yep.
This is kind of the conversation I wanted to have a little bit, but how did you do the initial firmware load? Did you preload firmware before you soldered the parts down?
So I actually put an ISP header on every board. So the AVRs are programmed with a 6-pin ISP header. It's like an in-circuit system programming header. And we had AVR ISP programmers, and we plugged them in and ran AVR dude scripts to load them up. So I did a lot of shell scripting. But it turns out that you can buy preloaded chips from DigiKey.
Yes, you can.
For a mere 20. It's like 25
more.
cents a chip or something. I think you could still beat that, honestly, but there's a lot of frustration you could avoid too.
It's almost not worth it, especially for like 1,000 units. If it's 10,000, but if it's 1,000 units, it's
Well, if you're doing other like test fixturing as well, right? So if you have like a jig where you plug in the board, you program it, and then you immediately run some tests, that's different than just plugging in and then programming.
It is.
Right.
Yep.
Yeah. So
I ended up actually ended up writing firmware for every board individually, and it was all sort of coming from a common baseline, because like I said before,
CO2 sensor board has a different code base than NO2 sensor board,
right? Because a lot of the uniqueness to it came from the fact that the naked sensors, they give you resistance, right? And they span a huge range. They span like kilo ohms to like tens of mega ohms during their response, right? And their responses are all individual. So they're all normalized by some factor that's unique to them. And all this is stuff.
Sorry, are you saying each one is individual or each different type is individual?
Each one.
One.
It's horrible.
So you have to characterize each one.
Wait, really?
So the problem is we didn't realize this going in, right? Because like I said, going into it, it was
How is it practical at all in industry though? Like who uses these sensors then?
Yeah, so no one cares about the accuracy of them per se and what they're actually used for. They're used in automotive industry, right? That's why they're less expensive, is because they're event detectors, really. Right.
So they have precision, not accuracy.
Right. They're meant to say, this thing is this engine muffler or whatever is behaving out of spec. Right, you're getting a huge spike of pollutants coming out of it. It's not meant to say gradually, right? So what we were thinking is that originally what we were thinking in this project really early on was we can neglect all of that. In the aggregate, all of this will wash away, right? But in reality, that didn't actually happen. I mean, you could still tell quite a bit by watching the time series data. You could sort of get a lot of good relative information. Mm-hmm. But the problem is the expectations in a project like this are really varied too, right? Like the people backing the project come from such a wide wide swath of life, right? There's people that are research scientists that are interested. There's people that are, you know, like my mom in her backyard, she wants to put it out there and not care about it. She just wants to contribute.
Right.
And there's like people that are real hobbyist enthusiasts, do-it-yourself people, right? They want to get into the code and like mess with it. So we were trying to suit all of these varied needs at once, and so that's a tough pill to kind of to get the message across to that whole community that like these sensors are all unique, and we ended up kind of after that, right, coming up with ways to normalize their responses. Because if you look at the data sheet, if you look at the data sheets for the sensors, they don't really talk about this, right? They just show you a characteristic response that's representative, and they give you sort of a span of response of the normalization factor for sensors. And the circuitry, right? I actually kind of, while I was designing it, I was looking at these things. I was like, wow, this circuitry has to hopefully account for this large span of resistance, right? Just making a divider, a single value divider, probably doesn't cut it because of the nonlinearity across the spectrum of resistances is too much.
Well, so even just if you're up in the mega ohms, you don't want to use a divider. So
yeah, right. Again, things I would have done differently
stuff.
Yeah, I would have probably put in a buffer somewhere in there.
Yeah.
But I actually made the circuit actually have sort of selectable. It was like a selectable divider. I had 3 resistors in series on the bottom side of the divider, and the top side of the divider was the sensor. And what I would do is I would in firmware turn on and off subsets of the base resistor by grounding nodes on the low side to give me sort of variable span. So even though I only had a 10-bit ADC, I had like 3 bins in which I could do 10-bit resolution. You know what I mean?
Mm-hmm. Yeah. What about the input impedance on the micro though too? I mean, if you're at the mega ohm level,
no, you're right.
You start to set up another divider there too.
Yep, it's true. So I think the input impedance on the AVR's ADC is like 100 mega ohms. So it's not that big of a deal.
Yeah, that's not too bad.
But like again, if I was to do it from scratch, right, I would have probably now put in some kind of at least a buffered amplifier.
Yeah, you had said when we talked before the show too that you were kind of some of these constraints were placed upon you, right? So you said cost constraints, and then it seems like also expectations of PPMs on the sensor. So like, did you not get a say in that at all, or what?
Well, I had a say, but I don't think I. So what I wanted to say is, like, let's just publish the resistance, right? I understand that the world really wants to know about concentration because that's what matters, and that's what kind of made me kind of concede on that point, which was like telling people resistance doesn't really answer the mail on what people want, right? People want to know.
No, totally.
Right.
So, but I also had this vision that like doing this translation at the endpoints on the controllers also wasn't necessarily the best place to do it either, right? Transforming, since the data was going to go up to the internet anyway, transforming it in the cloud, so to speak, would have been also kind of an interesting idea, right? Like sort of treating the individuality at a higher level, because the amount of processing that we had available to us at the low end was limited, right?
yeah. Linearization is not trivial. It's like, you need like second, third polynomial type stuff that could get real messy real quick. So.
Yeah. And I was actually doing fixed point math all over the place to try and do that.
Wow.
Yeah.
You're right. Yeah.
It was a real. There was a lot of weeds involved, right? Right way down in the weeds on getting all this stuff to actually. I actually encoded tabular transform curves.
Oh, no.
So I didn't do these polynomials you're talking about, Chris. I just made a table that was like
it's a lookup table,
right?
Interpolate between these values, kind of a thing.
Yeah.
No, that's how it's done a lot of times.
It's a perfectly acceptable way to. Perfectly acceptable.
So it's perfectly acceptable. Except remember the whole thing I talked about where I wanted to have add-ons and have the sort of interaction be abstracted over a bus and all that kind of a thing. Well, that meant that. In order to calculate a value, right, a parts per million value from the resistance, the master controller that was like sort of running the show would go out, first of all, discover that there was a sensor out there, right? So it would scan the bus, it would say, oh, there's a sensor at address 10 on I2C.
Mm-hmm.
Then it would say, oh, what kind of sensor are you? Then it would say, why don't you please tell me your entire lookup table so I can store it in my memory. Now, why don't you tell me your resistance? And now on the base controller, where I have sufficient resources to actually do the fixed point math, I could actually do the like lookup and interpolation problem. So
See, I would have done that right at the sensor microcontroller.
I would have done that too, except that we put a microcontroller that had 512 bytes of RAM and 8 kilobytes of flash on it. And it had to do the job of, handling the bus interface, handling the...
Yeah, but it's just a matter of paying an extra 30 cents for a bigger micro.
Agreed.
Right, with more resources.
Yeah. So like I said, right? I mean, like I think we made some optimizations at the wrong levels in some cases, right? Kind of lessons learned there. I agree with you now. In retrospect, putting a more powerful microcontroller at the node makes more sense.
That's always a good idea, right?
Yeah, well, I mean, if you can, like I said, so so fast forward to today, right? So we've continued shipping air quality eggs since then, and in the meantime, we've been looking for different kind of technologies for the sensors and re-architecting the whole kind of system because, like I said, all those hops to get to the internet are kind of there's so many chances for things to get messed up, right? Mm-hmm. So in the meantime, since all of that, I designed a board that has Wi-Fi in it called Wildfire. And so I guess I should mention, like all the stuff I've been talking about here is like open source, right? You can get all the CAD files, all the source files, everything. It's all out there. And so I designed a Wi-Fi board called Wildfire that has an ATmega 1284p microcontroller on it, which is way beefier, right, than the Mega 328. Mm-hmm. It's got like 128K of flash and 16K of RAM. And so like it's got much more kind of resources and capabilities. And it has a built-in CC3000 microcontroller or CC3000
an
Wi-Fi
SD card
and an SD card,
bunch of other stuff. Yeah.
And an external watchdog timer.
Hey.
Because now that
suicide mission.
Yeah, like once you fielded these things and you see, sometimes they lock up because you're using open source software and sometimes the libraries aren't perfect, right?
Yeah.
So actually, I made for the Wildfire. I actually made a custom firmware load for an AT-Tiny85 so that it can be kind of a programmable external watchdog. So you can sort of at startup tell it, I'm going to pet you no more often than once every second and no less often than every 30 seconds. And it'll, hold you to that contract.
Yeah, right. And it'll just yank on the power if people don't know what a watchdog timer is, that it can yank on the power, just reset itself if it doesn't get the pet within the 30 seconds.
Yeah, exactly. Yeah. So or just the reset line.
Yep. Oh, that too. Yeah. Right.
Yep. So there's that. So I designed this Wi-Fi board. We put that out there as a dev board that people can use. And we started looking at different sensors. We found a company called Spec Sensors that makes electrochemical sensors, which are different than metal oxide semiconductor sensors. They're a totally different measurement problem, right? They're like potentiostat controlled circuits, and so they're like microvolt kind of resolution changes.
Yep.
So I put together some software and boards and everything else to kind of drive those, and that's what we're basing the new version of the air quality egg out on, and we just kind of released. It's kind of a soft release. We're kind of a beta community of testers.
So is the idea that eventually, because you have this what you called egg bus, is that right? Egg bus or something?
Yep. So the egg bus was something that I think was it suited a purpose for the first version of the egg, but what I've done architecturally, I've made some pretty. I don't know. I guess I made some pretty big changes there, right? So what I'm doing instead of like having this add-on architecture, because that's another thing I think was making add-ons is really kind of nice. Making an add-on architecture is really nice,
Right.
in theory.
Right.
It feels
the
nice.
assumption
It feels
is
nice.
that
It feels like
everyone's
you're
going to
doing
do
it
it,
right.
right? Like that everyone's going to.
Yeah.
It feels like
Right.
you're doing the right thing, right? So you don't have to buy it all at once, and someone can pick up a new thing, and the concerns are separate and everything else. But then what happens in reality is no one ever buys an add-on. They just get them together, right?
It's the holy grail dream of modular electronics.
Right.
So modular electronics development. So it's the Altium model.
Yeah, exactly. So instead for the new version, what I'm doing is I'm making them completely self-contained, right? So the unit that is a Nano 2 and CO sensor, which is the first one we're releasing here, is a single egg that has Wi-Fi and that gives you that data. So it is isolated and reports data on its own, right? And so what we're going to do is we're going to come out with more eggs, and they're going to do their job, right? They're going to be individual eggs. They're going to collect their information into the... you'll be able to say, these are my eggs, these are my sensors, right? But they're all doing their own job, right? And they're also going to share sort of a pedigree in terms of a lot of the software baseline will be the same, but they're going to have individual sensor management code for them. The other thing that I did on the new one, which again is like, hey, if I had more computing resources and so forth, what would I do? Going back to version 1, I made it so that the software can be updated over the web. So like users don't have to actually know how to program a device to get a patch.
Yeah, right.
which when when we sent the original eggs out, of course there were bugs, right? Because there's always bugs. No matter what you do, there's always bugs. It's just the ones you don't know about yet, right?
Right. So would you say that your fault in that first version was just the assumption that all the users were like you?
Yeah, I mean, I think that's a fair way to put it, I guess. I think it's I think
that's a very common assumption, right? I mean,
Yeah. I figured that, hey, this is all based on Arduino. This is all based on stuff that people, in the circles that I run in are like, beginners can do this, right? But it turns out that when people are...
But they will they?
Exactly. You can make as many video tutorials as you want about how to ISP program an AVR. The number of people that are actually going to be able to pull that off are few and far between.
Right, especially when you have something where you want it to be a distributed network. You're probably not going to be able to find a distributed network of experts that are willing to work on your project and are interested in programming it. It's much more likely you'll be able to find a community of enthusiasts who might want the final output.
Yep. So I had this dream of like hacker spaces around the world supporting their communities and doing this kind of thing. But yeah, that's not reality, right? That's just not how things shake out usually.
It's not all of reality. It could be. It could happen, right?
No, it definitely happened for sure, right? There were pockets that, like Bristol in the UK, awesome. Like they were able to help a lot of people out.
Cool.
Chicago, same thing. I mean, like if you get into a sufficiently large population, there are people that are going to come out and do the help support role there.
Well, and I think the other interesting thing too is that so you mentioned like the fact that you're talking about architecture, I think kind of talks about the fact that you were doing the pro engineering stuff for a long time, thinking about that ahead of time.
Right.
But I mean, even when you're into the second version, you're still architecting it for reuse, but maybe not full modularity, right? There is a difference between those things.
Well,
modularity always requires big trade-offs.
Right. So, like for example, having it be open source in the first place, right? Having the way to program it be USB, that's a real easy way to like lower the barrier to entry on people that might want to modify it for their own purposes, right?
Right.
So your point's well taken. Modularity and sort of reusability are similar but not equal.
Right. Well, that's how you and I got in contact. You had written in actually after the last show about my discussion about firmware payloads and stuff like that.
Right.
You had said that you had a big problem with that because you had all these discrete nodes on a central controller, and then actually delivering that payload is difficult. What ended up happening there?
Right. So I'm trying to remember this conversation again, but the gist of it was that if you've got
I I think the gist was don't. That was your advice to me.
So that's kind of what I got at. So it's like it's kind of ties into what Dave said about like the Holy Grail and what kind of feels right, but what actually ends up happening is you end up with this. The interface has to be abstract, right, in order for it to be useful. And so making it abstract kind of inherently grows the complexity of the code that has to interact over it. You got two different interacting software loads that have to interface over this bus. Well, first of all, that's got complexity in it to start with, right? Second of all,
You're right.
Every time you add an interface, you add the chance for more bugs. that's right. Sort of I'm sure there's actual hard research that supports that. Even at the pure software level, right? There's people that have done research into reducing the number of interfaces reduces the number of code bugs that you have per whatever, some metric.
Probably per KLOCs, right? Kilo lines of code.
Oh yeah. Slack, that's what I remember.
Yeah.
They called it source lines of code.
Okay, yeah.
But kilo Slack, that's for like real big projects. And I don't remember the last project I worked on that had kilo lines.
Wait, you worked at a military company? Are you sure?
I was not a software engineer.
I was still my own hobby projects back in the programming back in the 80s and early 90s with 10,000 lines of code.
That's true.
No sweat, that was...
I kid, I guess. I'm sure that if you add up all the lines of code, it's way more than 1,000.
Yeah.
But anyway, yeah, I think that there's a sort of a threshold at which the complexity is merited, but you shouldn't cross that threshold probably until you have to, or until you have good reason to, until you've done the sort of trade-off analysis to justify it in your mind.
Well, when you say increasing the number of interfaces, though, you mean trying to squeeze everything into a single package, kind of like a single firmware payload kind of thing, or do you mean something else?
Yeah, I actually think federating the processing is... I think if you're going to do that, you should do it because you need to specialize, and it's code that's not going to change likely, right? It's going to be like code that's really stable, very simple, and isn't going to change often. If it's got the potential to change, you should try and, I think, make it fit into a single sort of programmable device.
See, now this is the kind of thing where I feel like we're going to have the comment section blow up.
Yeah,
because this starts to get into a lot of opinion stuff as well, right? Because there's a lot of...
I did this project and it worked fine for me.
Yeah, right. And I use an FPGA.
Right. But you know what? The other thing is the number of programmable devices you have equals the number of programming operations you have to do at manufacturing time too.
Oh, yeah, totally.
So, I mean, like, it all adds up. And like, I think that's something that's often neglected is like the actual impact to a project sort of on a number of fronts is related to sort of the number of programmable devices that are there.
Well, and I really do like the term federated too. I think that I don't think I'd ever heard that term before, but I'm sure it's just me not having heard it, kind of thing.
Oh no, I totally made it up. No, I'm just kidding.
Vic, the federated guy. Yeah, I know about him.
That's it. No, it's right. It's the idea that I think where it makes sense, where it's nice, is actually if you've got a small team of people and you want to find ways for them to all to contribute more. It's not the way so I think what I'm saying is
everyone can have their own module.
Yeah, exactly. And then you can spend time making it so they can talk to each other. But like the point is like that's something you do for that reason. It's not necessarily the right design choice.
Then you need more meetings.
No, that's right.
You need more like meetings about the protocol and yada yada.
Right, and that's what happens is things get really like bloated, right? The interface gets really bloated ultimately.
Well, one of the reasons I've done this in the past, have multiple processors for multiple things, is so that I can show milestones. This is big company stuff, right? So I can show that module developed, tested, proven. Here it is, documented. Right, move on to the next one. It's a milestone. I can show at the monthly meeting, tick.
Oh, yeah.
You know, right? That's another reason. Rather than putting all your eggs in the one basket, see what I did there?
If you will.
Right, and then, trust me, you know, every month I go, how's the progress? Trust me, it'll all pop out in the end.
Right.
You know?
So, Dave, in those cases, I guess in those cases, do those systems that you do that for stand alone?
They're like standalone modules, kind of like your eggs. You know, they do their one function, and then they report.
Do they have to be? Do they have to be under the control of some central authority?
No, they can. No, the central authority just basically says start measurement, and then it goes off and does its own thing, and then it returns data. So you know, it's like pinged. It's like do your job, give me the result back, kind of thing.
Yeah. So I'd call that a federated architecture for sure.
Yeah.
So did you usually use, what kind of buses did you use to do that?
Serial interfaces, not RS-232 electrical levels, but actual
like
serial.
RS-485 or something like that?
No, it was just because it was effectively on the same board, so you didn't need the voltage level translation of RS-484, and 232 or...
the huge swings like the minus 12
so
or whatever.
It was all done at the TTL level, but it used serial UART. So it was all, 9600 board kind of thing. And the reason I did that is so it made testing the module easy. I could test it with a PC and just hook onto the, just bodge in a serial cable in and then go to a serial terminal and then send it commands and boom, it returns data. And that's how I proved that the module worked.
No, yeah, that's a good approach. I like it too.
Yep.
Definitely for the DFM as well. I think the DFM is a big piece there, right? I mean, being able to say yes, this works. Yes, this is calibrated now. That kind of thing. Yeah, I think that's not designed for programming. Right?
That comes with complexity too, right? Like
it does. There's overhead in there.
And you've got to figure out what happens when I get out of sync with my master, or if I've got a byte that's out of phase, all that stuff kind of comes into play, right? And you end up having to write a lot of code that's resynchronization code that has nothing to do with your problem.
Well, see, in my one, it wasn't synchronization. It just sits there waiting for a command to start to do its thing, and then it goes, and then the module does its thing, and then it reports the data back, and that was pretty much it. So it was really
you wouldn't build in some kind of packet structure on it, or it's just
no. It was purely a command, and it returned all as serial text, serial string text. So
it's kind of like the AT command modem structure.
Yeah,
right?
so there's overhead there, but it meant that you could test and debug an individual module through a serial terminal, and you could have it print out debug text and self-test text, it's really nice stuff.
That's the C way of doing things, right? printf everything.
Right. Printf everything. Yep. Exactly. Yep. And and it worked. But if you were designing a module that had to if you design a product had to be put into high volume manufacturing, it's a piss poor way to do it, right? You just wouldn't do it that way. So,
yeah.
I wonder how this stuff plays into the satellite side of things too, right? Because I'm sure that you've been thinking big NASA satellite style, not necessarily the Planet Labs style, but it's going away, it's never coming back, it needs to be updated, and there's 25 teams working on 25 modules that all have to do their thing.
I suspect
that would
it's
probably be an interesting.
Extremely modular and high level in that respect. I think it must be. It must be.
Well, yeah. I mean, if they're on satellite, I guess I'm not sure about satellites, but I mean, when you need the reliability like that, you use whatever VME buses and things like that, right? Things that are industry proven, established, and deal with redundant processors on the same bus and things like that.
Oh, yeah. I'm not talking about the interface. I just mean how you actually split up, who's in charge, how you reprogram, that kind of thing. When you need to do a firmware update for something that's millions or billions of miles away, it's
Yeah. So actually, I made for Wildfire. I made a bootloader.
Oh yeah.
First of all, the 1284p has way more space for the bootloader sector. So it can be. So I made a bootloader that is derived from OptiBoot, which I don't know if you guys have heard of OptiBoot. It's like the bootloader for Arduino essentially. Okay. And so I took that open source baseline, and I derived a new bootloader from it. So I expanded the bootloader section of the chip. And the other thing I've got on Wildfire is an external SPI flash. So what I did is I made it so that bootloader can also boot from the SPI flash. And what I did is in the application code, I made it so that it can download an Intel hex file into the SPI flash, and the bootloader parses the Intel hex file directly.
So it's like a pass-through if you need to like a hard
so my
reset.
application just goes up to our update server and downloads an Intel hex file into the SPI flash, resets itself, and then the bootloader verifies the integrity of the SPI flash as a Intel hex file, and then says, "Okay, I'll burn this to my memory."
What happens if it has a bad hex file come through?
Well, I also include on the server, I include a check file, which has the size and the CRC16 of the whole thing.
Okay.
So before it decides to burn it, it says, obviously I could still screw it up by putting a bad hex file on the server with a bad check file to go with it.
Yeah, right.
And then right. So you have to kind of control. I see what you're saying. Like if you're in satellite,
no.
Right?
That's the level. Like I could mess something up spectacularly, and that would be something like how I would do it. But you can't protect for everything. So that's about as far as I expect.
Yeah, if you're going to like a Mars lander, though, you probably put all sorts of safeguards on it. Like there's probably parts of the code that they have to be fixed points or something, right? Like there has to be a dead beef written in this part of the memory.
Right. Yeah, but they have like lockstep stuff too. Like they're crazy. I didn't mean that level of it. I just meant if it gets a bad hex file off the server, puts it into SPI-ROM, and then it decides it's not the checksum,
Yeah. So the fallback then is you can still program it over USB. Right, so if it gets really hosed, the software is available, open source, and you can still like burn it again from.
You can always just remove the chip and just program it on a chip programmer,
take it out.
Come on, folks,
take it
it's
out
not
of the
that
dip
hard.
socket and whack it in.
There's a video tutorial.
I feel like I've been here before.
Oh goodness.
Yeah, but I don't know. I'm pretty excited about the ability to be able to push software updates to people. That's kind of cool.
Yeah, no, that's really great. Unless it's like a iRobot situation, you program the air quality egg to kill them or something.
Right. Oh no, the air quality egg has all 3 rules intact. It's
okay,
good.
Cool. And it
will do no harm to humans.
It does report. People can go check out the existing eggs online at airqualityegg.com and actually see all the nodes that are out there. So that's pretty cool.
And what is your web store? What is your Wicked Devices?
Our website's it's actually singular. I think the plural form works too, but we're Wicked Device.
Oh, Wicked Device. Okay, right.
Yeah. That's one of those things I've often wondered if we chose the right plural or singular on that one, but you kind of get what you got.
Yeah, Google helps. It's fine.
Because if it's singular, that implies you're a really small company. You've only got one product, whereas Wicked Devices, they must have more than one. Oh, they're huge.
Well, yeah, because you got the question like, what is the Wicked Device?
I know.
I'm like, no, that's not it.
Oh goodness.
Yeah.
And so how soon is the egg version 2 coming out?
So it's available for sale right now. You can get it, and we actually have a roadmap that'll be coming out with. I think we're going to come out with silicon dioxide and ozone next, and then particulate matter in September, I think. So we've kind of got a plan. We're going to roll these things out over time, and we've got a plan basically through the end of the year for every couple of months coming out with a new one.
Any idea how people are using this data then, like on the back end?
So there's a number of interesting ways, I guess. There's individual communities are sometimes kind of pooling their eggs and using them as a way to like look at relative changes in their local environment. There's a guy out in Colorado who is doing some research on the Grand Valley. So the part of the problem, right, that the air quality addresses is that there are like really expensive government run air quality stations out there, but they're few and far between, right? So the point of the air quality egg in many ways is to fill in those gaps, right? And to kind of see how air quality varies across space at a more granular level than, the 3 in New York State or something like that.
Right.
So there's a guy in the Grand Valley that wants to deploy a bunch of these to sort of demonstrate sort of how the airflow through these larger regions, right? Because of the geography and because of locations of various power plants and things like that. He's hoping to be able to see sort of a structural trend from having federated sensors. And there's other communities. London has a big population of eggs. Amsterdam has a big population of eggs. What I'm really still hoping for is for academics to really get their hands on these things and do sort of more statistical analysis. And citizen science is great, and it's like a big part of what air quality serves. It could really benefit, I think, from the cooperation with like PhDs and things like that are actually in the field that want to have an impact on real people, not just publish papers, right?
That's great.
It's a nice interface too. I like it. There's quite a few in Sydney.
Oh yeah,
it's like a map.
Yeah,
like
actually,
you go straight to the website and there's the map of all the eggs and yep.
And there's a couple of the new ones actually that have come out that we've shipped out to Australia, which is really cool.
I've got just one little thing. Why doesn't the color of the egg on the map change based on its value?
Oh. Well, that's a good suggestion.
It's programming, Dave.
It turns out that I do firmware, hardware, web development. So it's sort of a limitation of some of our development capacity there.
Right.
So are you looking for help? Because that's usually a good thing at the end of the show that if you're looking for people to help you out.
Hey, I mean, always, right? It's never hurts to make contacts with people, for sure. So if you want to email me, I guess my email address, you put it in the show notes. It's my name at wickeddevice.com. So victor.apria@wickeddevice.com.
Cool.
And I'll get it along to Dirk, who handles more of that kind of thing.
All right. Cool. Well, thanks for being on the show, Vic. It's been awesome.
Absolutely. It's been a pleasure, and I really, it's kind of surreal to actually, as a listener, be a guest. So appreciate you having me.
Yeah, it was good talking to you, and good luck with all the air.
Yeah. Hopefully we'll have an impact, and then it'll all kind of make our world a better place.
All right.
Nice.
Thanks, Vic.
All right. Sure.
Catch you next time.
Take care, guys.
Bye.